Okay, thank you. Yeah.
Okay. Good morning, everyone. Thank you all to attend to our Geophysics Department seminar. Today, I'm very happy to introduce you to Zhang, Professor Zhang from University of Vienna. I'm personally very happy to have Zhang here. Chi is my dear colleague since we were PhD students at Rutgers University. Yes. And from that time, we have always shared research interests. Yeah. And so today is something that we are accomplishing something that we have been planning for many, many years. Zhang is here to collaborate in our hydrogeophysics project of related to water and food security, which is funded by FAPESP under Professor Umberto from the Atmospheric Science Department. And Zhang, so she has done a PhD in Rutgers University, and then she went to Idaho Lab for postdoc, yeah, and Colorado School of Mines as a postdoc, and then she was hired as a professor in University of Kansas, and now she's a professor at University of Vienna. Yeah, so thank you, Chi, for being here and giving this talk, and please.
Thank you very much. Thank you, Andrea. Yeah, it's definitely my pleasure to be here. My first time in the South Hemisphere, also definitely the first time here. So very glad to be here to talk to you about my research interest, and also more importantly, how I can contribute to the CCT project. So today the topic is to talk about geophysical application from pore to watershed scale. And I want to focus a little bit on the pore scale for today, because this is some current interest in the research agenda we're doing now. But I will also show you some applications and some work we did before at the watershed scale, and probably can provide a perspective on how to connect the small scale with a large scale story. Or in other words, how to interpret the watershed data sets from a small scale investigation. And today I will focus very much on my recent research interest, which is NMR2. NMR stands for nuclear magnetic resonance. It's similar like what we're doing in the hospital when you have an unfortunate injury, and when the doctor take a look of your internal of your fluid intensive body parts. So we're going to do the same thing for the Earth material. So I'm going to walk you through some of the interesting things, and also some of the background of the research, and I hope this can resonate with many of you. So I know in this group here, at least I already see many people from the audience, you're very familiar with the critical zone and the groundwater problem. And for the critical zone, maybe this is just a repetitive information, but we're looking at so-called the Earth skin, from the bottom of the weathered rock or aquifer to the top of the canopy of the trees. In this critical zone, many people, including myself, focusing on two parts of the critical zone. The first is the architecture of the critical zone. For example, the structure, the lithology, and regolith depths. And maybe one of the most interesting questions people always trying to find, for example, is where is the bottom of the critical zone? And I know many geophysicists here using seismic and probably to delineate where is the bottom of the critical zone. But how those architecture is relevant to the water or nutrient flux, and this comes to this point about the critical zone function. And this is based on our understanding of the architecture, and then we understand the water distribution, the water storage, and the flux of water, sediments, nutrient, carbon, and also to interpret the weathering condition as well as how the critical zone can react to perturbations. So give you a little bit more detailed overlook of what I'm currently interested. So as Andrea just introduced, currently I'm in the beautiful Alps area, the beginning of the Eastern Alps. So Vienna is at the Vienna Basin, and literally the beginning of the Eastern Alps can be seen from my office window. As you probably know, the Alps is a very massive limestone mountain range, and many of our current interest is looking at the carbonate, which is very different from what the problem we're looking at in Extrema, for example. So we don't have crystalline basement rock, but instead we have a lot of the carbonated terrain rock. And for the carbonated terrain, I want to point out one thing is, maybe you know, you're not very familiar with this, but a carbonated terrain, one of the things is it reacts or weathered relatively faster in all type of this bedrock. And they were especially looking at how this precipitation and dissolution, this weathering, can be monitored using the geophysical method in order to predict the weathering pattern, and also to think about the entire carbonate terrain as a temporary global carbon sink, and how this reacts to global atmospheric CO2 cycle. So how about this critical zone and groundwater? And here I want to introduce you, I'm not going to say too much about this because we all know the importance, but I want to use this slide to opening up my research focus currently is in this unsaturated zone. So I've been working a lot in the past few years to especially focusing on interpretation of different geophysical signals in the unsaturated zone. So as we all know, for the saturated zone, and some of the well-established empirical petrophysical relationship has linked the geophysical observables to some hydrogeological properties. And this has been well tested, especially in sandstone and especially in some well-characterized aquifer. But for the unsaturated zone, as we probably know that, so the unsaturated zone, it's a very it's a very wide range of the area, which basically anything above the water table. And many of the geophysicists are focusing on the soil, and for example, looking at the soil moisture and link the soil moisture with the geophysical signals. And this is so-called a soil moisture monitoring. But this is highly linked with how much water absorbed by the plant, and also linked with evaporation, transpiration, and also rainfall and the interaction with the groundwater. However, one thing I want to point out is it's not so many people have been looking at, especially relevant to our Extrema watershed, is the water content in the weathered rock, so-called rock moisture. So we either look quite shallow, look at the soil moisture, or we look at aquifer. But from what I understand from my conversation with many group members here, so you've been really looking at how much water can be stored or can be distributed in the weathered rock, this rock moisture part, which can be varied quite significantly according to different seasons. So this is something we're been looking at recently. But then let's coming back to the soil moisture. So we know that soil moisture can be measured using many different ways in the lab or in the field. For example, if in the lab you use some very detailed balanced gravimetric method and to look at the water content change. And you can also use a tensometer or use a TDR. And the tensometer and TDR can also be applied in the field directly to take a look at this soil moisture content. And as we know that the soil matrix potential is associated with how much water you have. So basically, as the water content decreases, and you have a higher capillary pressure, and therefore the measured matrix potential, will, the absolute value will be increased. And in the field, we also use a geophysical method to look at the soil moisture. And I think this is also very relevant to many of this precision agriculture and smart agriculture we emphasize these days. And the geophysical methods such as GPR, ERT, or even larger scale EM method can be used to look at very shallow soil moisture distribution, like these two examples here. For this one is to use a GPR to monitor the soil moisture variation according to different seasons. And you can see this is depth here, the top 12 meters, and to look at this water content, volumetric water content distribution. And you can see this is quite sensitive. And even when the moisture is below 10% in terms of volumetric content, we still be able to use the GPR data to infer that. And this is a very famous, one of the early geophysical methods to look at the soil moisture. Maybe you were even introduced by this paper in your class. And in this one, particularly looking at the different vegetation routes cause the soil moisture variation using the ERT method. So this is some of the example here. And then I want to come back to this so-called rock moisture. As I emphasized, this is our focused research area for now. And if we think about the soil moisture, this is a very shallow top surface of the layer. But when we think about the rock moisture, this is broadly defined, but you can think it's any water content stored in the weathered rock. It can be from saprolite to all the way to the beginning of the bedrock. So if we look at the soil moisture variation, this is one of the very quite a high-profile paper published by Daniel Rampe and Peter Dietrich back in 2018 in the PNAS. In this paper, they use exactly the borehole NMR to look at this rock moisture seasonal variation, and link this seasonal variation to some large-scale hydroclimate data, and argue that for certain vegetation type, like those trees here, and their roots still be able to reach the rock moisture even during an elongated drying period. So this gives another implication of the hints to the groundwater management, basically saying that in some of the area, the vegetation available water content is still really high, regardless of the hydroclimate condition. So this is quite an interesting work, but this work opens a door for many of the questions and people back to answer. For example, how much the rock moisture you can install at different place. This is a hill slope experiment, very similar to the extrema profile you did. And some other question can be, okay, we know how much water content we have, but how does this water content distribute? Are they in the fractures? Or they're more in the small pores? So with those questions, many people have done some experiment. Now today, allow me to use some of our examples trying to answer those questions. So this comes back to this tool that I've been introducing, called nuclear magnetic resonance. And to start with, I'm trying to give you a brief overview of how the NMR can be used in near-surface geophysics. So in the near-surface geophysics, basically NMR tools can exist in 3 different ways to measure. First, we can do the benchtop lab-scale NMR measurement. And this is low field, 2 megahertz or 12 megahertz. For example, this is the setup I had before when I was in Kansas, but now I have a more powerful one, 12 megahertz, which can allow us to make some spatial distribution of imaging measurement. And we can also have the borehole tools, and these tools, I think many of you probably have heard this before, and this is a tool that we're trying to get here from Vienna to USB to IAG. So this is going to be exactly the setup you're going to see when this arrives here. So this tool basically is a probe. This probe has internal magnets, and these internal magnets serve as the background magnetic field B0. And when you deploy this probe into your borehole, they have a sensitive area about 12 to 15 centimeters, so can sense the water content and the distribution within the radius of 12 to 15 centimeters from the borehole. And it depends on how deep your borehole is, and this probe can be deployed to different depths, and you can measure at different depths, and the interval will be minimum 25 centimeters. So this borehole NMR, I'm going to introduce later why this can be very useful. Similar to the lab NMR, the borehole NMR and the lab NMR, all the surface NMR, all of them have one unique capacity, which is the unique sensitivity to water content. So if you have a resistivity data, which you cannot tell if it's coming, the high conductivity part, if it's coming from clay or it's coming from water content, then the NMR can tell you for definite if it's a water content contribution. So this is a unique capability of NMR, this unique sensitivity, which we leverage a lot in many of the geophysical surveys. So if you do a joint geophysical surveys, you have ERT and you have seismic, you have GPR, and you have other things, but you want to know about the absolute water content, then NMR can be really helpful too. And we also have the surface NMR. The surface NMR deployed using using some large loop, just directly put on the surface of the ground. And this one, it's not like this two, which has their internal magnetic field. This one leverages the Earth's magnetic field. So how much of the background of your field site Earth's magnetic field is the intensity level of the surface NMR. So for example, I was talking to Andre yesterday. So for example, in Vienna, we have a 48 micro Tesla, the magnetic field strength in Vienna, because it's the latitude is about north 42 degrees. So I think here the magnetic field will be much smaller. So almost half, yeah. And we were talking about the data yesterday, so maybe this is one of the important reasons doesn't contribute to strong signals here. This is the 3 ways of NMR and how to use it. And maybe I will use this opportunity to talk a little bit about the principle of NMR to help you better understand, to think how this can help your research. And the NMR, and it works like this. I think this should be sorry. How can I go back? Oh, yes. Oh, I thought this should be a cartoon, but it's not moving, but it's fine. So NMR works, you put your sample in a permanent magnetic field. This magnetic field called background magnetic field B0. As I introduced in the lab, you probably have 12 megahertz or 2 megahertz. And in the borehole NMR, you have about 450 kilohertz, and in the surface NMR, you have much less of the magnetic field. And then when the experiment starts, you need to have an external radio frequency magnetic field pulse to excite your proton within your sample. And the measurement actually starts once you remove this external radio frequency pulse. And then the proton will relax back to the original status where it was in this background magnetic field. And this time for proton to relax back to its equilibrium status within the B0 is called relaxation time. And it depends on the direction. We measure the longitudinal direction and the transverse direction. And we call that relaxation time T1 or T2. And we use this time as a characteristic parameter to infer, first, the magnitude of this relaxation time is determined by how much proton you have, therefore how much water you have. And the second, the duration of this relaxation time is determined by the pore size in your sample, and therefore the pore structure. So you can use this information to infer, first, how much water you have in your sample, and the second, how the water is distributed within the pore structure. So this is an example showing here the different distribution of the NMR signals. And in this exact exact case here, this is actually a drainage experiment in some of the very porous limestone samples. And the first curve here is the fully saturated condition, and we let it drain, and we can observe how the curve is redistributed. Therefore, we can understand where the water is moving. So this is the NMR principles. And I gave you some examples from the literature, how people using NMR, and some of this directly relevant to the CCD project, because you also took some surface NMR measurement. So this is one of this experiment did in France, and they called Oscar Critical Zone Network. Is also one of the quite famous hydrogeophysics network in France. And in this experiment, they did a surface NMR in a cast unsaturated zone. So very similar to the example I'm going to introduce here. This is also focusing the Vadose zone, but in a casted region. In this place, this is where their geological setting, and this is their experiment. This the experiment site, and in the top one here, you can see this is sample the signal amplitude from surface NMR, and here they didn't plot the distribution of the relaxation time, only the amplitude of the signal. And what they did here is a very preliminary comparison between the signal amplitude and the precipitation events. So you can see this roughly that matches when you have the precipitation event, and the amplitude of surface NMR also increase. So this serve as a demonstration that surface NMR can be used for the long-term monitoring of the water content in the subsurface. And there's another surface NMR application. I intentionally choose the surface NMR application because I know you've done some surface NMR, but if the data can be very helpful, is still in question, but just use this example to explain. And this is Antonin Lukashenko's work back in 2013 and 2020. And in this work, they did this surface NMR on top of the Mont Blanc. So it's a very nice place, and they look at the water content in this cave that in this glacier surface. And this is the experiment they did in 2019, and then they did some further experiment to look at the signal distribution back in later in 2020. So this also shows that even in a glacier environment, and when you look at underground unknown object and trying to understand how much water within that, and this shows a very promising 3D review of the water content in the subsurface. And so there's another example, and this one is using the surface NMR and the borehole NMR together, the joint application of this critical zone problem. In this work, I think it's very similar conceptual framework like the Extrema example here. They use a multiple geophysical method. First, to use the seismic method, you can see this, to use a seismic method to delineate the saprolite thickness. So this is from the seismic velocity distribution. And after that, they use a surface NMR to look at the large area water distribution, and then use the borehole NMR to constrain the surface NMR water content estimation. So therefore, to get a water capacity, or you call water content distribution in this entire area. And therefore, they can calculate how much percentage of the water is in the unsaturated aquifer, and how much of the water in the how much water in the weathered bedrock, and how much of the water in the fresh bedrock. So this is how they leverage all the data set together, and also to show the value of both surface and borehole NMR. So with this being said, next I want to talk about some very detailed work that we've been doing, and this is under revision for WR, and this is this is going to be very technical, but this is focusing especially on the challenges how we interpret NMR signal when it's in the unsaturated condition. So similar challenges happen for different type of geophysical method, and for NMR, it's especially a challenge that if we want to understand how the pore structure affects NMR relaxation in different saturation status, there's no current framework to help us interpret that. And the second challenge is, and this is especially important for some of the carbonate rocks that we're dealing with, which is the pore coupling effect, meaning that the water can transmit between different pore space, and how we can quantify and interpret this process or this phenomenon using the NMR signal. And the third challenge is, how about the information about the multi-phase flow? One of the good example is when we have a contamination or oil spill, and you still get some signals, but how the signals is reacting in terms of the NMR response, and how we can differentiate which part of signal from the oil, which part of signal from the water. So this is related to this three major challenges. I think one thing I want to also to talk to you is how currently we are solving this problem, and this is probably have to bring you back from the field, coming back to the lab, and even smaller scale. So currently, the way we are trying to solve this is to build some pore scale numerical modeling, and to understand at very small scale and how different processes dominating the signals. So using these two charts, these two figures, I think I can try to explain what we're trying to do here. So when we're trying to understand how the NMR signals respond to the pore structure, usually the first thing we do is to take a CT image, a micro CT image, to get a real representation of our porous medium. So this is becoming our routine work to acquire some of the CT image of the natural porous medium, and to look at the liquid, solid, and vapor phase, how they distributed in different pore space. And starting from here, we construct our realistic pore structure. And this realistic pore structure will be something, a representation of pore network from this. And sometimes we can have some idealized pore structure. For example, we just set up our synthetic pore structure, such as spherical pore structure or triangular pore structure, and trying to understand some basic phenomena from this idealized pore structure. And what kind of factor we're interested? We're interested in the pore size, pore shape, as well as water retention behaviors, or you call the imbibition or drainage behaviors in the different pore structure. So this is a very small detailed work, and trying to understand how all of this impacted the NMR signal. This is some of the interesting work we have done. That's the revision I was talking about. In this case here, and we understand if we have a small pore, our NMR signal will relax very fast. If we have a large pore, the signal will relax very slow. It's translated into our field observation, meaning that if we see a very long relaxation time, 2 to 3 milliseconds, it's very likely to indicate you have some free water, either in the fracture or appear on the surface. Or if you have some microseconds or even nanoseconds of your signal, it's very likely that this water resides in very tight pores, for example, in shale. And we see this all the time. And sometimes we have a bimodal distribution of the rock fracture. And this bimodal distribution can have some pore structure at nanometer scale, and some of the pores at millimeter or even centimeter scale. And you see very distinct two peaks in your NMR relaxation time. And one is corresponding to very small pores, and another one corresponding to the large pores. So I think this is a very useful and a very intuitive tool to help us understand where your water resides. So in this work, and we're trying to understand better in this situation, either the small or large pores, how we can interpret such pore size distribution in the unsaturated condition. So we have done some of this modeling work and trying to simulate a different scenario. For example, we considered lithology. We consider if it's a sand, if it's a clay, and how much of the surface is reacting with a proton. And we also consider the pore network connectivity. For example, if we have a large pore and a small pore, and they're connected by some pore throat. If you don't have any the induced polarization IP work, you're probably familiar with such a setup. And this is where I also think there's an organic link with the IP work. So we consider the pore network connectivity and this pore throat connecting two pores, and how the proton is relaxing between the two pore space. And then, of course, we have to consider the throat length and the throat width in order to simulate this connectivity. And then here is some of this published literature, and to show how the connectivity is controlling the different NMR response. And this is also showing how the surface geochemistry controlling that. And some of this are experiment data and some of the simulation data. And in the last part is the third challenge we're currently working on, is looking at the multi-phase flow impact. And the multi-phase flow impact, as I mentioned before, we're mostly concerned that in our hydrogeophysics contents is organic materials contamination. So, for example, here or in this diffusion T2 relaxation curve, and we can differentiate. This is a water diffusivity around 2.89 times 10 to negative 28, and then this is oil diffusivity. So we can use this 2D measurement of NMR to differentiate the water and oil. And Andre, as I told you yesterday, so this borehole NMR we can use in Extrema also have the capability to measure the 2D in the field. So theoretically, if in the field we have oil and water mixed situation, we should see some signal anomaly associated with different components. This is also some of these examples and how we can use a different NMR technology to differentiate different fluid. So basically, you can consider as a fluid typing technology to tell you if it's water, if it's oil, or even the methane of the different gas component. And so, for example, here you're looking at one of the measurement we can do is a T1, T2 spectrum, and the T1, T2 spectrum can differentiate the water and oil, and also look at the DT2 as the example shown earlier, also to differentiate water and oil. So this is some of the directions we're working on, and I want to show you some of the challenges we see in the experiment. So here, some of the experiment, for example, in the sandstone or in the bentonite, in the unsaturated condition, as the saturation degree decrease from top to bottom, and we see the peak of the NMR signals overlapping, and then you won't be able to differentiate anymore if this is from the small pores or if it's a large pores. All the interpretation can be misleading. So the current work we're trying to do is to correct such misinterpretation like this one here or this one here, because obviously this doesn't make any sense if we think what they argue here. This is a small pore filled, the small pore filled with water in unsaturated condition, and this curve at the bottom, this curve here is a saturated condition. So literally, this interpretation means the small pore can have more water when it's in the unsaturated condition, which is counterintuitive. So such misinterpretation is actually very common in NMR-related literature, especially in terms of interpreting the field data. So we find out this the roots of this error, and we establish a new method, a framework to interpret this unsaturated condition. So this is another of the example, basically saying that in unsaturated condition, the small pores can absorb even more water than the saturated condition. Obviously, such interpretation is problematic. So our recent work is to use this numerical simulation, as I introduced earlier, to start from a pore structure and either an idealized one or the real one, and to use a finite element method to solve this Bloch-Torre equation, and in order to understand the magnetization distribution in the space, and in order to calculate the NMR response. So this is one of my PhD students' first chapter of the PhD. So I'm glad this has been going quite well. This is our simulated data. I'm not going to the detail about this, but basically this is telling us a framework and how we can establish a new interpretation framework for unsaturated NMR signals. And this is show some of the direct output from the simulation result as a saturation decrease. And this is a different pore shapes impact, and this one is spherical and this one is triangle. And it is quite interesting to look at the triangle pores versus the spherical pores, and also give us indication that if we have very good data sets, very nice signal to noise ratio, and we probably even can tell from the NMR signals if your pore size is more to a triangle one or to a spherical one. So this is the work we've been doing, and this is some detailed simulation and how we simulated different scenarios, a different combination of the pores and a different shape, and trying to understand how this contributes to different NMR signal. So this is how we establish this new interpretation framework, and to correct some of existing literature's results. And in this one here, we use this new framework to apply to two case studies. The first case study is a silky sand, the silty sand. And in this one here, we apply our new interpretation method and to correct their over-interpreted small pore saturation. So as you can see here, this is their interpretation, which is problematic because at lower saturation, the small pores obviously has even more water than the large pores. And using our framework, we'll be able to help to separate this signal here, which is also attributed to part of the large pore saturation. And similarly, we have done this framework for another case study in the limestone samples. And this is actually our own published work. So it's a trajectory of research. So in 2020, we thought our interpretation is right. And now in 2024, we say our previous interpretation was wrong. So this is the current work we're doing, trying to correct this interpretation and to get a more realistic distribution of the water content. So this one, I want to highlight the importance of this one, because this one we did both of the field work and the lab work. So we'll be able to link the field study with the lab scale investigation. And such interpretation framework then essentially can be directly applied to the field to help us to further constrain our field water content distribution interpretation. To imagine that if we use this in the field, then we can very confidently say that this part is coming from at lower saturation. Very likely in this dry season, we have some lower saturation. And if we have the saturation degree around 60%, and even within this, and almost 1/3 of the water still coming from the fractured water content. So this will be a real significance and implication of such framework application. Yeah, so to wrap up with this part of the story, and I've been introducing some of this simulation work we have done. So you probably can tell, we've done a lot of this laboratory measurements, and also trying to link with a field scale, and eventually, definitely we want to link with either conceptual or numerical hydrological model from the entire watershed to leverage the hydroclimate data and also to use existing monitoring wells data and to put all the data sets together to build a very good conceptual model to understand the water flow. So with this, I think there's a lot of the remaining science questions. So I think some of these questions you've probably also been wondering. For example, the structure, heterogeneity's impact on the flow and the transport of the water at a different scale, and what is the weathering rate, and how is the porosity and the hydraulic conductivity evolved during the weathering, and so on. But some of this, I think they're probably more critical for the carbonate critical zone terrain that we're investigating, but some of this is probably universal for any of this critical zone problem that we're all dealing with. And actually, I also prepare some, I think it's almost time, but sorry. Yeah, 10 minutes. Yeah, I also prepare some extra slides, but I put in hide. Can we? Oh, yeah, maybe we can just exit this. Yeah. Yeah. Can we? No. I hide the slides. Can we? Hide them. Yeah. Can we unhide them? Yeah. No. It's no. I hide the slides. Can we look at the slides itself? Yeah.
Okay.
Yeah.
PowerPoint.
Exactly. Yeah. I think this is fine. Can you go up? Go up. Yeah. Go up. Yes. Up. Maybe starting from 30. Yes. Maybe starting from 30. So. Sorry. This is because due to the time constraint, I was not sure if we still have time to discuss this. We don't need to project, just show. Yeah, because it's a hide. So yes, from 30. So this is actually this is a project. No, you don't need to project. Yeah, because you cannot do that. Sorry. So this is the work I've been talking to the CCD program project about the work we have done in a smaller watershed in Kansas. But it's very shallow and has interbedded limestone and shale formation. And so the problem we're dealing with in general is the same as the extrema case. For example, we're trying to understand where is the water flowing. It's also inspired by some of this monitoring wells observation. So in this watershed here, as you can see, this is very small. I think Andrea is probably smaller than your N15. This is only 2 kilometers, and the 2 kilometer scale this is really small one. But even in this very small watershed, we had around 33 monitoring wells and over 30 years of hydroclimate data. So we have precipitation data, we have temperature data, and a series of this hydroclimate data. But the question is similar. So when they did some of the tracer test, so put in one of this monitoring well and trying to expect to recover some of the tracer in the downstream, but they never recovered. So it's lost. We don't know where the water is flowing and how it flows. So can we go to the next slide?
Okay.
Yeah. So this is similarly, I'm not sure if it's exactly similar to extrema, but this place here has established a long-term ecological research site by US NSF in middle of Kansas. And can you go to the next slide? Thank you. And what we did is something similar to what you've been doing here, and trying to think, oh, geophysics probably can help. So we have done, you can see surface NMR, borehole NMR, ERT, JPR, and we also have done some of seismic, but a longer profile. So actually not showing here. And then we're trying to cover upslope, mid-slope, a valley, and also trying to cover follow the stream. So upstream direction and downstream direction. Can you go a bit lower? Thank you. Yeah, so here, I'm not going to tell you all the data sets, but I'm trying to focus on NMR. This magnetic field is similar around maybe 42 microtesla here. And the surface NMR, we did several lines here, and they're trying to be close to our ERT line, and also trying to close to some of the monitoring wells. And the surface NMR, we group them into upslope, mid-slope, and the valley. And obviously, in the valley, we have the highest water content. And also, in this valley area here, we find out about 15 to 25 meters from the surface, we have the highest water content preserved in the shale layer. So this is very interesting. We never found this before. So that means the top surface can be very seasonal varied, but the shale layer in the deeper formation actually are the main reservoir to preserve a lot of water even during very long drying period. Sorry, can you go to the next one?
I cannot stream these slides, right?
It's okay. If you want to do that, it's also fine. Yeah.
It's okay?
Yeah.
Okay.
So this is our published work. And so this one also has been verified by the borehole NMR. And this is something I really hope that we can achieve in Extrema here. So this borehole, yeah. I think it's 34. Yeah, slides 34 probably. Yeah. Yes, thank you. And this one here, so basically answer one of the questions we always had when we look at the ERT data, when we look at the resistivity distribution, if this is just some clay or if some water content. So the borehole NMR data really help us to answer that. And this is also quite beautiful data, especially look at this here. This means we're seeing two of these strong signal anomalies. And one is this associated with very small pores, which once again to verify the clay or the clayish formation have this water content. And one is associated with more of the large pores, which verifies our idea that some of this very weathered, this lithology control, very weathered limestone can also hold some water in the large pores. And this part of the water are very likely to be evaporated during the dry season, or to be transported to the different aquifer, but not this one. This one still remains. So this similarly here, you have the small ones and you have the large ones. Next slide, thank you. And there's some detailed comparison between the surface NMR, borehole NMR data, and the next one. And this is the last slide I was just trying to say. Then we can put the borehole NMR data together with the ERT data and to use this to help us to constrain the interpretation of ERT. Sorry, can you go to 30? Yeah, this one. And then later, as I mentioned to some of you before, we also took a core sample from the monitoring well to come back to the lab to do some of this drying experiment to simulate in the field if we have a dry condition, how the water is actually drained. So we did a lot of this laboratory study and to combine this together. So if you say any fit or any need to do some of the laboratory NMR and to help to understand the drainage pattern, I'll be very happy to do so too. Yeah, I think that's it. Thank you. Yeah. Yeah, I think it's more trying to tell you what do I do and to throw some discussion to say if any future collaboration or current collaboration also, and to see how I can fit or how I can contribute. Because I think some of the experience we had, of course, like all the experience, most of the time it's a failure. And some not so bad ones we put together as a paper, but it still has so many questions and unanswered. Now, for example, this work here, eventually we failed to really construct a very nice hydrological model. We had some very good ideas, but there are some details are still not cannot be put the pieces together. So yeah, we're still on this place a nice hydrological model. But hopefully you can have your own extreme hydrological model to leverage all this data sets you have. Yeah. Yeah.
I have a question.
Yes. Yeah. Sure.
Thank you for the presentation.
Thank you. Yeah.
It was very nice.
Yeah.
One issue we had here was the presence of magnetic rocks.
Yes. Yes. Yeah.
I was just wondering, in the simulation parts, could you take that into account?
Yes. Yes. That's a very good question. And can I use the mouse?
Yes. Well, the mouse is there.
Yeah, okay.
You can.
Okay. So this is a mouse?
Yes.
Oh, okay. Yeah. Thank you. Yeah, I'll just use this. Sorry, I didn't know this. I'll show you this. This is a. If you recall, this is a. This cannot go back. Okay. There's a. So
You can use this as a mouse using this button here.
Can I go back? Go back.
The mouse is
Yeah,
here.
go top. Oh, okay. Oh, thank you. I try. Yeah.
Then you can.
Okay.
Okay.
Yeah. There's a block equation, Pore block equation, which I can show you here. Oh. This requires fine motor.
You can click it on lower on the bar. It's going to. Yes.
Okay, this is much better. And you can see.
What slide do you need?
I don't know. I have to probably lower, maybe 20, maybe slide 20.
Here?
No, the slide 20.
Thank you. Okay, thank you.
Not this one. Sorry. Can we go a little bit? Yes, this one. Sorry. Go up a bit. Go up. I'll go up one more. Yes. This one with the equation, 22. Yeah. Yeah. So we definitely can do this. But there's some problem. So that, as you said, the paramagnetic issue. So basically, we treat this so-called off-resonance frequency. So it's off-resonance frequency coming from two sources. One is a chemical shift, which you definitely cannot see using the low magnetic field. But another one is the inhomogeneity of magnetic field caused due to the presence of paramagnetic material. This can be done, but this actually can be tricky. So you have to change this, and this the paramagnetic field also give you a magnetic field distribution in three dimensions. So we currently haven't considered this, but this can be done. Yeah. So this is a long answer and for your question. Yeah. Yeah. So theoretically, yeah, definitely this can be done, but very few people have done this because it's a very troublesome to introduce this additional off-resonance frequency. Yeah. Yeah.
Effects also appear when the NMR measurements are taken with probes. The whole on for measurement on surface.
All the measurements, they will have impact. Yes, but the good thing for the lab NMR and the Bohr NMR is you already have your own internal magnetic field. It's just much stronger. And so you will see some signals, but from this noise, but you'll be able to do some calibration to quantify, to eliminate this. But for the surface NMR, maybe even localize the paramagnetic material can contribute to as much as the background Earth magnetic field. Yeah. Yeah.
When you do lab measurements, you take a core from the field. How do you make sure you don't impact the pore distribution?
That's a very good question. So the samples we're measuring in the field are mainly coming from two type of material. One is an unconsolidated soil sample, and another one is consolidated rock sample. So this problem definitely arises much more for the soil sample because it depends on how you repack them and how you rearrange this. Yeah, we just have to accept this is a limitation, and you have to replicate the situation at least to be consistent throughout your experiment. But for the consolidated sample, as what the one I showed for the limestone, sometimes you see the very big pores. It's not fracture, but a very well developed secondary porosity due to the limestone weathering. And those samples, they are very fragile, but still you can manipulate this. And you saturate it with a different fluid, and you're trying to look at the drainage pattern, and this can be easily done. So I would say the rock sample is much easier to deal with than the soil sample. Yeah, and I'll be happy to make some measurement for extrema, and if we think there's a value to quantify how the water is drained in the subsurface, if we have some sample. Yeah.
Well, thank you for this clear and detailed explanation.
Thank you.
Well, I have told you I have a concern about water content across the watershed.
Right.
And that's that's the main interest of the surface hydrology group. That composes with the geophysics interests, which is weather, soil, and groundwater.
Yep.
And I have heard from my colleagues at geophysics that their methods will tell us very much about structure and parameters of ground, of aquifer structure, but not much about water content. And that's my main interest. And I was very impressed, correct me if I'm wrong, that your method can tell us a lot about that. Not only
I hope so.
not only in amount of water, but available and not available water for evaporation. That's right?
Yeah.
Okay.
That's really the hope that we can achieve this. Yeah. And to be honest, Umoto, and when I talk to many of the group members, I'm also very impressed by how comprehensive this project is. How much data set you have already collected. And I think you will be able to build a sophisticated hydrological model at the end, which I'm really jealous.
Yeah. Well, you're welcome to join the group, of course. Yeah. So we have measured soil moisture down to 1 meter for a long time.
Yeah.
And also have gases of evapotranspiration using eddy covariance and land surface models. So we have this other bunch of estimates that can complement to soil moisture distribution. So my question is, before my question, I also saw you showed a picture from a paper using GPR to measure soil moisture. That's new for me. I didn't understand you could detect soil moisture from GPR, but in terms of watershed, horizontal variation and vertical variation, can we elaborate on a plan that captures how much of this water is distributed, how much water is near the springs emergency, or upstream in the recharge zone?
Right.
I think that's very important for the whole contest. Okay. First, because these springs they are often distributed in slopes, very well defined slopes. There is in Brazil enforcement law that restores vegetation near the springs. Yes.
I already learned from some group member told me this.
Yes, and also at the ridges, in up to the recharge zone. So so we would like to learn which are the consequences, or how much can this restoration can expand or not, or how can that affect this the soil moisture infiltration and the groundwater recharge at the end, at the very end, dynamics of water flow movement. So my question is, if over the next 2 weeks that we'll be here, and I extend that question to my colleagues here, if we can elaborate on a plan to use different methods,
Definitely,
at least on a seasonal basis,
sure,
get this picture, and look at the whole idea, at the whole month.
I absolutely. I think I'm really very, very interested in this project and also the topic, especially after I seen some of the geophysical data. And I also feel, because still back in the States, and I've been closely follow some critical observatory work, and I think that there's some experience we can borrow, and maybe some of, for example, to relate it to the question you asked, I think you probably see the example I just showed. At that Kansa observatory, this very small watershed, they have a lot of this groundwater data in terms of temperature and also isotope. And I think many of the questions in terms of the rate flux, this can be really better interpreted using that. But the geophysics, of course, should give us set up our boundary condition, a framework where things are, at least. And maybe there are some different, not only the methodology, maybe some better, some alternative places for measurements, and can be really set. But I think this really, I really like all the data I've been saying. It's really fantastic. and at least we see anomalies, we see signals. Maybe at the current stage, it's not very consistent how we interpret them, but I hope maybe by, you probably know that the probe gonna stay here for at least a year. so maybe with the help of some different tools, and we can better answer some of these puzzling questions, and to really isolate the factor. I also think it's really interesting, scientifically a really interesting problem too.
Okay, it's good to hear you're positive on that. Okay? So let's keep on working.
Thank you, Umberto.
No more questions?
Okay. I'll be here for the next 2 weeks, and I'm very happy to talk to each of you. And I'm also really, seriously, I'm really impressed, and I think it's a wonderful team here. It's great.
Thank you for the wonderful talk, Chi.
Thank you, Oh, and just a little shameless self-plugging. My current office is in 212. So if you want to stop by, feel free anytime, and we can grab coffee or lunch together. Thank you very much.
Thank you.